Hello everyone, let's solve some Leetcode today. So today we have Leetcode 42, that is trapping rainwater. In this problem we have been given n non-negative integers which represent the elevation map where the width of each bar is 1 and we have to compute how much water it can trap after raining. So it will look something like this. Here we have an array that is 0, 1, 0, 2, and this is representing an elevation map. Okay, what this means is that if we start here on this line, then the first block is 1 width height and its height is 0, right? So there is no block right now. The width is 1 width, but the height is right here 0. Then we have a block of 1 height. So the height is of this block is 1. Then we have another 0 height block. So here we don't have any block. That's why the rainwater can come and trap in here. Okay. Then we have a block of height 2. So as you can see here that the width is 1, but the height is 2 for this block. Then after this we have a block of 1. So as you can see here we have a 1. Similarly we have 0 again. Okay, so this particular block, this have a height of 0, but as you can see that the amount of water it is holding is basically twice. There are 2 units of water here, right? Now the next block has a height of 1, as you can see in the array. Then we have a block of height 3, just like this one, and so on. We have the next block of height 2, then next block of height 1, the next block of height 2, then again next block of height 1. So in this way we have been given an elevation map, or basically a map of height of each block that is present in this line. Now, whenever the rain will happen, some of the water will trap in this structure, right? So some water is right here, then some water is right here, correct? Then some is right here. Now we have to figure out how much water the structure will contain after rain. So let us start with starting, okay? So here the block is height 0 and there is nothing on this side. Yes, there is a particular block of height 1 here, but there is nothing on the left side. It means nothing will stop the water from the left side. It means the whole water will simply go away. What it means is that there will be no water in the first position. We can always ignore this position safely because there will be no water here. Then we have a block here, okay? Now how much water can we store on top of this block? Well, nothing, right? Because there is nothing on the left side that is going to hold this water, right? Yes, there is a block on the right side that can help hold the water, but there is nothing on the left side. So all the water that will hit the top of this particular block will again go away. It will not stay. Now we have this block and it actually contains some water. So the reason it is containing water is because there is a boundary on its left side that is helping it to hold the water, right? So the boundary of height 1 is right here. And then there is another boundary of height 2 right here, which is helping to hold the water. So the amount of water here is basically equal to the boundary here, right? You can also try to do 2 minus 1, that is 1. So that is also equal to the amount of water that is being held in this particular position. But we can see that the amount of water can never exceed the minimum of this boundary and this boundary. If the water try to exceed and actually comes here, the water will simply go down, right? Because there is nothing on the left side at this height to hold it. So eventually the water will always and always and always be equal to the minimum boundary height. So till now we encountered 1 unit of water. Now from here we will shift to this particular position. So now we are on this block. Okay, how much water can we actually store on top of it? 0, right? Because there is nothing on the left that is going to hold it. Yes, there is a particular block that can help to hold it, but there is nothing on the left, so it will simply go down. So here also we have the 0 water, right? So we can shift to this particular block and we will see that we have some water on top of it right here. Okay, we have a 1 block of water, and the reason is that there is this particular block of height 2 that is holding this water in place, and then there is also this particular block that is actually helping to hold this particular block of water. How? Well, suppose that if this particular thing did not exist, this entire section did not exist, what do you think will happen? We will simply have this particular block and this would have been just shifted right here, correct? If this would have been shifted right here, then you can imagine how this particular block will actually help to hold this block of water, because this particular height will make sure that the water does not slip away somewhere. And so here the height is 3 and here the height is 2. And if this block did not exist, if this entire block was just empty, what do you think the height will be for the water? It will be 2 blocks, right? But right now it is not 2 block of water, it is just 1 block of water, because 1 block of water is actually blocked by this below land, right? So what you can say is that we are going to find the minimum of this, and we are going to subtract the height of the block that we are currently on. So 2 minus the height of this block is what? 1. So it means we are going to hold 1 block of water on this position. So now we have one more block of water. So now we will shift to this position and we will try to find out how much water can this particular position hold. So the height of this position is 0, right? So to figure out the amount of water that we can hold on top of this position, we will see that, okay, we have a block of height 2 right here, right? And then we have a block of height 3 right here, which is the maximum heights on left and right side. So what we can try to do is we can try to imagine that these blocks did not exist. Then what will happen? We would have a block right here and then we would have a block right here, and since this block do not exist, what will happen is that these two blocks will actually come closer to each other. So this block will come closer to right here and this block will come closer right here, and then we will see that we have these boundaries. So right now we have a boundary of 2 here and we have a boundary of 3 here, and we have this particular block right in the middle. So it means the height of this particular block will depend on the height of this one and this one, right? So the minimum between 2 and 3 is 2, correct? It means the water cannot exceed the height of 2. So we will have 2 here, and now we have to subtract the height of the land or block that is present in this position. So the height is 0. So we will subtract 0. It means we will get 0. It means we can now add 2 into our sum of water. And now we can move on to this position. So here also we will try to assume that we only have 2 blocks of maximum height on left and right side. So we can shift this block right back to where it was, and this block will be shifted here. So we are basically isolating this block to find out the amount of water we can hold on top of it. So right now again we have a height of 2 here, we have a height of 3 here, and it means we will have to take the minimum. So 2, and then we have to subtract the height of this block, right? So the height of this block is 1. So 2 minus 1 is equal to 1. It means we have again a water amount of 1 here. So now let us move on to the next position. And here we can see that on this block, we want to find out how much water we can hold. So what is on the left side? Nothing. The maximum height block on the left side is right here, 2. But the height of this block is 3. So it is going to be above 2. So there will be nothing on the left side that is going to help hold the water on top of this 3 height block. Similarly, on the right side, we don't have any block that is going to hold the water for this particular block. So it means there will be 0 water on top of it. Now we move on to the next block, and here we see that we don't have any water here because yes, there is a block of height 3 here to hold the water, but there is no block on this side that can actually hold the water, right? So there is no block of height greater than 1 that can hold the water on top of this block. So we move on to the next position, and here we see that we have a height of 1 and we have a boundary of these 2 blocks. The height is 2 here and the height is 2 here again. So we have this one block between 2 blocks. So we will have this one block of water. Why? Because left boundary is 2, right boundary is 2. So minimum between 2 and 2 is simply 2, and 2 minus the height of this particular block is, well, 1 is equals to 1. So 2 minus 1 is equals to 1. And so we will now end up adding 1 right here. And I think I did not add this particular thing, so I will also add 1 right here. So now we will move on to this block, and here we will try to find out how much water we can store on top of it. So yeah, there is something on the right, this block, that can hold the water on this particular height, but there is nothing on the right. So it means all the water will simply go down. So we won't have any water on top of this block. Then we will move on to this particular block, and here you can see that we have something that we can use to hold the water on top of this block, but there is nothing on the left. So it will again go down. So water on top of it will also be 0. So it means we have this much water stored in the particular structure, which is equal to 6. And that should be the answer. So as you can see here that 6 is the answer. And this is how we actually have to figure it out. So whenever we wanted to find the amount of water stored in a particular position like this, we would just take the maximum that is present on the left side, and we will take the maximum that is present on the right side of this particular position, and we will take the minimum of them, right? So 2 was here, 3 was here, I took the minimum, and then I just subtracted the height of the block of land that was on this position. So right now it is 0, so I will just simply do 2 minus 0 is equals to 2, which will give me the amount of water that is stored on top of this position. This much, right? So it is 2 blocks of water and I got 2. Similarly for this position also, the maximum height on the left is 2, the maximum height on the right is 3, and that's why we will take the minimum, that is 2, and 2 minus the height of this block is what? 2 minus 1 is equal to 1, and this one represents the height of the water block that is above it. So what it means is that in order to find the water at the highest position, we need to find out the maximum height of a block on the right side and the maximum height of the block on the left side, and then only we can figure it out. So it means we need to store these heights somewhere, right? So we can have 2 arrays, max left and max right, and in these arrays we will store the maximum left at a position I. So on this position here, what is the maximum height of a land in the left side, and that we can store right here, correct? And in the same way we can store the maximum heights for a particular I on the right side. So in this way we will have 2 arrays that are going to store the maximum in the right direction and in the left direction for a particular given I. So we will have a left max array, we will have a right max array, and we will optionally have a minimum array also. So you can calculate the minimum on the runtime if you want to. Otherwise, you can store the minimum values in the array also. So we will start with this position. What is the maximum on this side of the 0? 0. There is nothing, right? Then we will shift here. What is the maximum on the left side? Now left includes this particular position also. We are going to do this. We are going to include this particular position also. So we will have 1 right here. Then what is the maximum on here? It is still 1. Why? Because we have this 1 and this is 0. So maximum on the left side is still 1 for this particular position. Then we will go to the 2 and now the maximum is 2, right? Because 2 is greater than 1. Now we will go to the next position. We will have 1 and now the maximum is still 2 because 2 is greater than 1. Again we will come here on 0. The maximum is still 2. Then for this also the maximum is 2. Then here we come and we get the maximum as 3 because 3 is now greater than 2. So now we will move on to the next position, 2 here. The maximum is still 3 here. Then for the next position we have 1. The maximum is still 3. For the next position is 2. The maximum is still 3. For 1, the maximum is still 3. And now in the same way, we are going to find out the maximum at right at each index I. So here, what is the maximum at right? Well, if we include this one also, the maximum on the right is 1. Then we will go here. The maximum is 2 now because 2 is greater than 1. So we will have 2 here. Then the maximum for this position is again 2. For this position is again 2. Then for this position, the maximum is 3. So we will have 3 here because we are including this position also to calculate the maximum. Then here we have 1, so we will again have 3 as a maximum. Then here we have 0, 3 will be the maximum. Then here we have 1, 3 will be the maximum. Here we have 2, 3 will be the maximum on the right. Here we have 0, 3 again. Here we have 1, 3 again is the maximum. And here we have 0, 3 again is the maximum on the right. And now we can calculate the minimum between these two values, the right max and the left max. So the minimum between 0 and 3 is 0. The minimum between 1 and 3 is 1. The minimum between 1 and 3 is again 1. Here it will be 2, 2, 2, 2, and then 2 again, 2 again, then 2 again, then 2 again, and here we have 1. So now we have all the information that we need to solve this particular question. In order to find out the amount of water on the ith index, we can simply take the minimum of ith index and then subtract the height of the block, the height of the ith index block from it, and that will give us the amount of water that we can hold on the ith index, just like we were doing in the earlier dry run demonstration. But guys, as you can see that it is going to take order of n time complexity. Why? Because we are going to store n elements in this, n elements in this, and then n elements in this. So is there a better way to actually do this? Yes, yes, and yes. You can remove all the 3 arrays and do this in order of 1 space complexity, which sounds crazy because you need all these numbers to calculate the minimum. But yes, you can actually do in order of 1 space complexity because there is a trick here. So till now we know that in order to find out the water on any given position, we need to find out the maximum on the left and the maximum on the right and find their minimum and subtract this particular height. That we understand very well. So what we can try to do is we can try to use 2 pointers here. Yes, it's a very tricky question to use 2 pointers, but that's the thing about it. This is a hard question. Here you need to be tricky. Okay, so we will have 2 pointers here, P and Q. Okay, now just think about it. The maximum on this left side is right now 0. Correct? And the maximum on this right is what? 1. Correct? And we also know that we cannot store any water on the end of the array because there is nothing on the right side to hold the water, and here there is nothing on the left side to hold the water. So it means the water storage will only happen in this particular section. So now we will again have a left max variable and a right max variable. These are going to store the maximum on the left side and the maximum on the right side. So first of all, we are going to start with 0 and 0. Then we will take these values right here, 0 and 1, and we will place them here. So left max will still be the 0. The right max will become 1. And now we need to move these pointers somehow, right? So which pointer are we going to move? P or Q? Well, whichever is the minimum. So right now the left max is minimum. So we are going to move the P here. So P will be on this element, on 1. Now for 1, the maximum left is 0 and the maximum right is 1. But we don't need the maximum right. Why? Because we know that this particular value, the left maximum, is actually smaller. And what it means is that even if there was something smaller than 1 here, suppose there was something 0, we would not care about it, right? Because we need the maximum on the right. And if there was something greater than 1, suppose that there was 3 here, actually, because we don't know whether there was 3 or there was some other element here. But even if there was something greater than 1 here, we will still not care. Why? Because this left max is the bottleneck. This will decide the maximum height that the water can take. Do you understand this thing? It is like this. We have two boundaries, okay? So it doesn't matter how big this particular boundary is. It can be 5, 10, 20, but the amount of water that we can hold here is going to depend on this particular minimum boundary, okay? So whichever is minimum between this and this, that is going to decide the amount of water that we can hold within these two boundaries. And that is why right now we have left max less than the right max, and that is why left max is going to decide what is going to be the amount of water that we can store on this particular position. So it is 0. It means we are going to store 0 minus 1. Okay, so it is going to give us -1. So -1 does not make sense. So whenever we will get negative values, we will simply make them 0. So right now we have 0 water stored on this position. Then we know that we have 1 here and 1 is greater than 0. So we will again update our max left and we will have 1. So now the left max is 1 and the right max is also 1. So which pointer should we move? Should we move Q or should we move P? Let us move Q. So now the Q is right here on this position 2, right? So what is the amount of water that we can store on this position? Well, we are going to take the minimum between the left max and the right max. Since they are both the same, so we will end up taking 1 anyways. So 1 minus height at this particular position, that is 2. So 1 minus 2 is equals to -1, which will end up getting 0. Why? Because we are going to ignore negative values. Now since we have 2 here, so the maximum on the right side is going to be 2. Okay. Now we need to shift the P because the left max is actually less than the right max. So we will shift the P here. The P will come here. And now what? What is the amount of water we can store here? So here again it will be depending on the minimum, right? So here the left max is the minimum. So we will simply take the left max and subtract the height of the current element. That is 0. So it is going to give 1. So right now in our sum we got the first one, okay? Then we will again shift the P because this 0 will not update the left maximum, okay? So the left maximum will remain 1 and the right maximum will remain 2. So what is the amount of water that we can hold here? Well, the left maximum is 1, okay? So we are going to do 1 minus 2, that is -1, which is equal to 0. So we cannot hold any water on this position. Now we know that we have 2 here. So the 1 will be updated to 2 here. And now we have both of these same, right? So we will just update the P again. So P will come here. Now what is the amount of water we can store here? We are going to do the same. Okay, we are going to take the 2 with the left max and we will subtract 1 here. So it will give us 1. So it means in the sum we will again add 1. Now we will again shift the P because they are still the same, okay? So I'm shifting P here. And now what is going to be the amount of water we can store here? It is going to be the 2 minus 0. So 2 minus 0 is equal to 2. So we will add 2 here. Now we can again shift P to here because these are same, the left max and right max. So now what is the amount of water we can store on this position? Well, we will again take the left max 2 minus the current height of the block, that is 1, equals to 1. So we will add 1 right here. Now let us do something different. Let us shift Q here. Okay, so Q will be right here. Okay, what is the amount of water I can store here? Well, it is going to be the right maximum minus the height of the current element or the current block. So right maximum is 2. So 2 minus 1 is going to be 1, right? So we will get 1. Simple, right? So now we can again shift Q here. So Q will be here. Okay, now what is the amount of water we can store here? We are going to take the right maximum again. So the right maximum is still 2. So 2 minus 2 is going to be 0, right? So at this position we can store 0 element. And now since we are getting 2 here and there is already 2 here, so I cannot update the right maximum still. Now I will take the Q here, I will shift it right here. So what is the amount of water I can store here? Well, I am going to take the right maximum, that is 2, and I will subtract 3 from 2. So 2 minus 3 is equal to -1, which we will simply consider 0 because we are not going to deal with negative answer. So now we have 3 and 3 is greater than 2. So right maximum will become 3 here. Now we know that 2 is less than 3, right? So we will have to shift the P. So P will be shifted, okay, and P will come here. Now P and Q are at the same position, so it means that we will simply stop the loop. Now we don't need to run the loop. We have found the answer. We will sum all these numbers and we will get the answer. So 1 plus 1 plus 2 plus 1 plus 1 is equals to 6. And that is our answer. So now do you understand how we are able to actually remove all that extra array space and we are able to do the entire calculation in the order of 1 space complexity? That's a crazy trick, right? And I was not able to figure this out by myself when I was trying to solve this question. Like really, this trick is really hard and you might not be able to figure this out in an interview also because there is a time pressure of 45 minutes and to find out these kind of things, you will need to think about the problem for quite some time. So this is the kind of problem that if you have already seen it, you will be able to do it very quickly. Otherwise, it will take you a lot of time to figure out this kind of solution. So now let us look at the code. So left pointer is set to 0. The right pointer is set to the ending element of the given height array. and then we have the left max and the right max variable. So left max in the starting is going to be the height of the L pointer, the right max is going to be the height at the right pointer. Then we have water here is 0. Now here is the loop that we are going to run. So while left is less than r, so as long as the left is less than r, we are going to run this loop. So if the left maximum is less than right maximum, we know that we need to shift the left pointer. So I will take the left pointer and shift it to 1. Then I will calculate the left max. So it is possible that the current element at left after shifting is greater than the value stored at the left max. So I will just update the left max first with this particular line. And then here I will simply calculate the water, and because of these two lines we will never get a negative value. How that will happen, I am just leaving it to you figure it out how this kind of thing actually make a difference. And then in the else block we know that the left minimum is going to be greater than or equal to the right minimum. So we are going to take the right pointer, we are going to shift it by 1, and then we will update the right max right here, and then we will directly update the right max, and then we will calculate the water. These two lines make sure that we do not get negative values here also. And how that is going to happen, I am going to leave that to you. Okay, now once that entire loop runs, okay, which means the left will become greater than or equal to r, we will know that we have gone through the entire array, and so we will simply return the water that we calculated till now. So now let us try to run this thing and see what happens. So our solution runs in 11 milliseconds and beats 71.05% solutions on Leetcode. It is also passing all the 324 test cases. So our solution is pretty efficient. Now let us look at the space and time complexity for this particular solution. So the space complexity is going to be order of 1 because we only have left max variable, right max variable, then we have left pointer, then we have right pointer. And all these variables are simply integers, right? The space that these variables are going to consume is going to be fixed regardless of the input size. So input can have 1 million elements in the array, and these are going to consume the same space, and that means they are fixed, which also means that they are constant. And that's why we are saying the space complexity is constant. The time complexity is order of n. Why? Because we will have a left pointer, we will have a right pointer. Okay, the left pointer will go in this direction, the right pointer will go in this direction. The left pointer can at max go through the n element that are present in the array. The right pointer also at max can only go through n elements that are present in the array. So it means together they will travel n plus n elements, which is 2n. So order of 2n elements is going to be order of n, right? Because we will simply remove the constant in big O notation. And that's why the time complexity is order of n. It is 2 pointer, guys. The 2 pointer is supposed to give you order of n time complexity. So yeah, like the video, subscribe the channel. If you have some kind of question that you would like me to target, or you have some kind of topic that you would like me to talk about, just let me know in the comments. Now we will meet in the next video. Till then, bye.